Hello.
Yes. So welcome everybody to the second talk of today. So the second talk will be delivered by Dr. Dibya Chakraborty from IIT-Madras, and she's going to talk about inflationary models in string theory.
Thank you so much. Hello, everyone. First, I would like to thank Anish and Dibya for organizing such a weekly seminar. It's really useful. And thanks for giving me this opportunity to present my work. So today I'm going to present to you two inflationary models. Inflation, which we already know by now, that inflation is a period of accelerated expansion happened in the early universe. And I'm going to embed such scenario in string theory, and in particular type 2b, the flux compactification. So string theory, we know it has 6 extra spatial dimensions. So in my talk, it is a string cosmology talk. So I'm going to show you how this string theory, how from string theory I can arrive at a potential energy, because we already know that we will be interested in potential energy driven inflation. So my aim will be to show you how to derive this potential energy and how we can have this accelerated expansion. And how this string cosmological model usually stand out from others is the following, that in our model, we have a physical origin of the potential as well as the scalar field. So the scalar fields I'll be working with, they are the volume inflation and the fiber inflation. So the volume modulus and the fiber modulus, they are actually volume of this internal space. The 6 extra spatial dimension, that the volume of that geometry, the geometry that lives in this extra dimension, that geometry will give me that scalar field. And not only that, there are various other string cosmological inflation model, string inflation model available. But the way our work is, again, is favorable. I will try to motivate you why our work is favorable as we go on in the slide. Okay, so I'm going to talk to you about volume inflation as well as fiber inflation, and these works are based on these two papers. One is in JCAB and the other one in Physical UD. And this work is done in collaboration with Swagata and Pramod from JC Bose and George from University of Wyoming. Let's proceed. So in my talk in abundance, you will hear these 3 words. So I will be talking about inflation, which is again a period of accelerated expansion. We all know by now. So within a very brief amount of time, the universe is expanded by 10 to the power 25 order, as we can see from this plot. And I'm going to embed that in string theory model building. So what do I mean by that? So I will consider a particular type of this 6-dimensional geometry, which I'm trying to show you here because it's very hard to draw a 6D. So I will have a K3 fibered Calabi-Yau. So in this K3 fibered Calabi-Yau, I will have a, which just means that this K3 fibration, it has a 4-dimensional complex manifold and which has a 2D base. Sorry. Oh, yeah. So you can imagine, like on this 2-dimensional base, on each point, this K3 fiber will sit. And in one of the inflation, which is fiber inflation, this K3 fiber will stretch and squeeze in space and give us the accelerated expansion. And the other case, which is the volume inflation, here this whole 60 volume will stretch and expand and give us the volume inflation. So my scalar field, which is often people also call moduli. So this moduli in the 10D, that is our 4-dimensional world plus 60. So in the 10 dimension, after you dimensionally reduce, that is you get rid of your extra dimension, this moduli from the 60 becomes scalar fields in our 4-dimensional world. So this scalar field, so one of these scalar fields, it will be related to this 6-dimensional volume. Hence the volume inflation, we will study volume inflation with it. And the next case, we'll have this K3 fibration will act as the inflator, hence the fiber inflation. Okay. So now we are already being motivated by Dr. Suratna Das that why we need inflation, but let me just talk about the horizon problem briefly. So what you are looking at is the cosmological microwave background, which we know how it was created. So at the time of decoupling, there was a time of decoupling when the photons, which were trapped inside the atoms, they were started to roaming freely and started to come towards us in all directions, creating this cosmological microwave background. Now one can ask this question that what is the largest size of the causally connected region at the time of decoupling, and what angle it subtends at this CMB sky today? So now we can see that that angle is just 1 degree, and two points, if we consider 2 points which are separated by just more than 1 degree, they should have different behavior and different behavior in terms of temperature. But that's not what we see today. So we see that if we consider two antipodal points separated by even 180 degrees, then those 2 points are also sharing the same temperature modulo 10⁻⁵ anisotrope. So we know from laws of thermodynamics that in order for 2 points or two particles to have the same temperature, it has to be in some causal contact at some point. It has to be in thermodynamical contact, right? But it did not happen if we go back to the time of decoupling. Not only that, if we look at this light cone coordinates, which is just constructed out of this FLRW metric in conformal time, then if we extrapolate back at the time of tau equal to 0, that is the time of Big Bang, even then those light cones do not interact, do not intercept each other. So the size of the forward light cone and the size of the backward light cone, they do not match. So what does inflation do? Inflation stretches this conformal time back to infinity in a way so that these two light cones match. And how much inflation we need and when to exactly stop the inflation, that we calculate by measuring like how much we have to stretch to solve the horizon problem. Like how much from tau equal to 0, how much we stretch so that we solve the horizon problem, we make the light cones contact. Okay. So that is one of the pivotal role that inflation play in solving solving the problem of lambda CDM model, which we know is a standard model of cosmology. Okay, so now what is how theoretically you can model inflationary model, like you can build inflation is the following. So this is, I'm showing you inflation in its minimal form, where you have a scalar field minimally coupled to gravity, which means there is the Einstein-Hilbert term does not have any coupling of the scalar field. So you have a scalar field slowly rolling down to its minimum and reheating. So we will not be talking about reheating in my talk, but one can study that obviously. So the scalar field will slowly roll down the potential, and when it is slowly rolling, this part, inflation will take place. And once it stops, once it rolls down really fast, the kinetic energy dominates, the inflation stops. Now, slow roll inflation, in order to build, again, theoretically build a slow roll inflationary model, you usually solve this equation of motion, which is Clyde-Gordon equation of motion. And then when to stop the inflation, you usually take this slow roll parameters, which is often related to the Hubble parameter, Hubble expansion, which is related to the expansion of the universe, and how flat you need your potential to be, which is usually relevant for single field models of inflation. So we can just directly look at epsilon v and eta v. And when it becomes 1, inflation stops. And not only that, inflation doesn't just solve horizon problem, it also gives the amplitude of the power spectrum. So if you take two different points in the CMB sky, and if you take the power spectrum out of it, if you take the correlation, then the amplitude of the power spectrum that inflation predicts, it matches with the Planck data. And it can also gives almost scale invariance of the power spectrum. So this is related. This is encoded in this NS parameter known as spectral index. And this is again constrained by Planck data. And inflationary model can actually goes. You can see this in this plot that there are various inflationary models which can actually satisfy those data. So this is 2 sigma 95% confidence region and 68% confidence region, or the other way around. Sorry, I always make this mistake. Anyway, and it also produces the primordial gravitational wave, which is again, it is upper bounded by the Planck data, and it is not been observed till now. So there is just a bound on the tensor to scalar ratio, the primordial gravitational wave. And this quantity is again very important. This tells you how much how much acceleration you need and how long you need to solve the horizon problem. Remember, I was telling you that I have to stretch the light cone. So you can explicitly calculate how much you need to stretch the light cone. Anyway, and this phi star is the pivot scale. So it is the scale in the Planck data, like it is the scale where the error bars in that matter power spectrum, the black body power spectrum, where the error bar is the lowest, that denotes by this pivot scale. So all these values that you are seeing are all calculated at this pivot scale. And this 60, so there is one catch. So the total amount of inflation can be anything, but we need from this 5 star, from this k star equal to 0.05 megaparsec inverse till the end of inflation, when this slower bandwidth becomes 1, that that value of n should be 60. The 5 star could be anywhere. So you need the minimum 60 folds of inflation. The total amount of inflation can be anything. Okay. So now, so in this plot, what I'm fleshing out is the following. So there are various single field models of inflation that one can have. Toy models of inflation, such as natural inflation, then alpha attractor, as well as for m square, 5 square, 5 to the power 4 inflationary models. Actually, alpha attractor has some physical origin. Anyway, so what I'm showing you that the single field models of inflation, toy models of inflation, they're absolutely in agreement with the Planck data. So now, what is the main motivation to go beyond? Well, we know that contrary to the standard model of particle physics, in standard model of cosmology, that is lambda CDM, we cannot consider the gravity to be static. So we know that the gravity is dynamical there. And not only that, like the energy scale of inflation, that is the scale where the quantum gravity constraints can become important. So, and we also know that we have a prediction from the quantum mechanical side as well in inflationary models. So we need a theory which can combine both quantum mechanics as well as the gravitational theory, general theory of relativity. So string theory is one of the leading candidates which can do that. And in this string theory, one can not only have one scalar field with physical origin, it can give us several scalar fields which can drive this inflation. Remember, I told you that you need a scalar field to drive inflation because we are interested in scalar field potential driven inflation. So it gives us both the potential energy as well as the origin of the scalar field. And it can, like I said, it can give us a plethora of scalar fields. It helps us as well as it causes a problem because one has to make sure that you are stabilizing. By stabilizing, I mean giving a positive mass, giving a mass to the scalar field, and so that it does not play a role when the universe is inflating. So there is no time dependence. So I would like to have this inflation if we are interested in inflation models as well as other scalar fields that coming down from string theory compactification. So one has to make sure, except the inflaton, the other fields are stabilized at this minimum. It is not a very trivial job, so one has to make sure of that because otherwise they will mediate field forces. And we know from tabletop experiments, they are highly constrained. So yeah, one has to make sure of all of that. So it has caveats as well as usefulness. Okay, so string compactification in a nutshell. So here, this is our 4-dimensional 1 time and 3 spatial dimension. On top of that, I will have 6 extra spatial dimensions, and hence this construct the superstring theory, which is a 10-dimensional theory. And if you have more spatial dimension, we will go to the bosonic string theory part, and it has, we know, total of 26 dimensions, but it lacks the chirality. So the chiral theory was the superstring theory, hence we are interested in that. And upon quantizing this 10-dimensional superstring theory, we can get this 6 types of string theory, and the present focus is this type 2D string theory. And after, I mean, we know that the physical, the highest physical scale is the Planck scale. So between Planck scale and this string scale, there lies the high energetical string theory, all this type 2B, type 2A, and so on. And below that, I will have a 10-dimensional effective field theory whose mass, whose mass spectrum matches the 10-dimensional supergravity theory. And after dimensional reduction, I will get a 4-dimensional effective supergravity theory. And I will be interested in that. And when I dimensionally reduce, so I have this 10 total dimension. And in this 10 total dimension, I have 4 dimension cross this 6 extra spatial dimension. And when I dimensionally reduce, I get rid of this 6 dimension. But all these topological details, all this geometry and the fluxes that you add in the 10 dimension, that is going to carry forward, and it will be manifested in this scalar field that I'm talking about that will drive the inflation. So not that the information is also lost. Okay. And I'll be also interested in Calabi-Yau threefold because of the supersymmetry, lack of supersymmetry there. And okay. Now, we will consider Calabi-Yau threefold, which has 3 complex dimension and total 6-dimensional space. We don't know a metric because we know in order to study inflation or dark energy, we need to write down an action. And in that action, you have kinetic term and potential term, right? And in that kinetic term, you need to have some metric. I mean, you have this GAB there and del phi A, del phi B. So you need to know this GAB usually. But in Calabi-Yau, we don't know that. But what we know is the following. So we know how many sub-manifolds there are, like how many cycles. So this, I have 6 dimensions. Now inside that, we can have several cycles, such as 2 cycle. And this 2 cycle is particularly important in my talk because those will give me the scalar fields, which is the scalar moduli, which is related to the volume of the internal space. Then there can also be 3 cycle and the universal field, which is the axial dilaton related to the string coupling. So in my construction, I will be considering this complex structure moduli and this axial dilaton, 2 types of scalar field to be stabilized at their minimum. And I'll be interested in studying the dynamics of only the scalar moduli. Okay. So now, the idea of the talk is the following. So I will address the modular stabilization because I already told you why is this important, because otherwise they will play a role. And I will see a lot of scalar fields lying around in today's world, and fifth force, they will mediate fifth forces. And I will see if I can get de Sitter in string theory, de Sitter vacuum in string theory, because in order to study reheating, if you want to study reheating, then de Sitter vacuum becomes important. And I will add perturbative corrections, which I'm going there slowly. And if we can find this de Sitter vacuum, then I would like to study what is the inflationary implications. Okay. So now this is a busy slide, but it is not so complicated. Okay. So what I'm showing you is the following. So I started from 10-dimensional effective supergravity, type 2B supergravity. Then from there, I dimensionally reduced. And I told you, right, that all this information, they are not going to be lost. So this information, they are actually encoded in this superpotential and Kähler potential. And using these two, I will be constructing my 4-dimensional scalar potential, which is a function of this inflator for my purpose. And I'm like, it will be a function of other scalar fields as well, but it will be a function of my inflator as well, this scalar potential in 4D, and which I will construct using the data from the string theory side as well. And from the so this is the non-perturbative level. So this is the tree level. So the tree level Kähler potential is a diagonal, it takes a diagonal form of its scalar fields. So from the very construction, we can see that, so this T denotes the Kähler moduli, which is related to the volume of the internal space. And also it will be our inflator. So this, we can see that from the construction, this PFT goes to 0. So if you just simply plug in, I can go back, yeah. So if you simply just take a 2 derivative of this, so volume can be written in terms of this T plus T divided by 2 or something. Then if you take a derivative of this volume and simply just plug in here, taking the covariant derivative, then if you do this simple calculation, you will see that this the scalar potential for this scalar moduli drops out. So in order to stabilize the scalar moduli, one needs to go to step 2. That is, one needs to add some more correction. And that's what we call it, like we are adding quantum corrections. And that's where the famous KKLT construction and the LVS construction. So KKLT because of the names of the authors, and LVS because of this large volume scenario. So those constructions come into picture when we add these quantum corrections. And our whole purpose is to write down a potential which is non-zero in Kähler moduli. Okay, so the goal is the following. So I will add, because it was a flat direction, there was no potential generated for the Kähler moduli. Now I will add the quantum correction and I will generate a potential, but usually it has been seen that they generate an anti-de Sitter minimum. So we need to have some ingredients to uplift to a de Sitter, and one has to make sure that one does not uplift too much so that it gives the runway. Okay, so these are the things one has to make sure while constructing this type of scenario. And I will have one direction. I will have I will choose one direction. Usually people choose what is the lightest scalar field in this scalar potential. So I will displace it from its minimum and I will let it roll down to its minimum, giving us the needed acceleration in the universe, early universe. Now, what are these quantum corrections? So these quantum corrections can be of perturbative nature as well as non-perturbative nature. And in this perturbative nature, one can have two types of corrections. One is in inverse string tension, which goes as this, and the other one is in string coupling. And these are the names of these corrections, and I will show you how they look like. Now, there comes like why our scenario. So I will be presenting to you now a perturbative large volume scenario. So large volume means the volume of this internal space is large. And large is compared to the previous scenario, which was KKLT, which was studied in the literature. So large is not large compared to our four-dimensional world. In the four-dimensional world, it is still not, it is still hidden. I mean, hidden in the sense it is still small. But large compared to other construction that was studied earlier in the sixth dimension, in the sixth dimension. And these large volume scenarios are needed. They are always well motivated because they can help us to control several corrections such as the supergravity corrections, as well as when I get the four-dimensional effective filter, they are well under control if I stay in the large volume classical regime. And it was so in the standard large volume scenario, the way that people have got this large volume is by an interplay between, actually I will show you, yeah. So let me just go here. So there was an interplay between this is the perturbative correction and this is the non-perturbative correction. So usually this large volume, due to the presence of this exponential, this large volume was obtained due to this interplay between perturbative and non-perturbative corrections. But these non-perturbative corrections are not well understood from a 10-dimensional picture. It is debatable, but usually it is not very well understood. That's why if we can find a construction where I can still obtain this large volume, but without the need of non-perturbative effect, then that would be favorable. So let us see. So I will not be adding any non-perturbative corrections. And these are the corrections, that is this perturbative corrections, and this is an inverse tension correction, and this is the loop correction. So this is the set of four corrections that I will be adding in my perturbative constructing in the hope to constructing a large volume perturbative large volume scenario, and we will see what is the implication for inflation. Okay, so I have already explained large volume scenario, but let me just say it one more time. So here I have one perturbative and one non-perturbative, and the exponential volume is obtained because there is an exponential sitting right there in the favor of the potential. Okay. So now what I'm going to do is I will deviate from this large volume scenario. I will add no non-perturbative effects, and there will be no non-perturbative effects, and I will also take a different form of the volume, because in the large volume scenario, the volume is this, where if you can see, so this is the total volume is written as a bigger, I mean, it's a four cycle volume, four cycle minus there is a large cycle and there are some small cycles. And these small cycles are basically hollow cycles. So if they increase in size, that will decrease the overall volume. And if this tau L, which is the large cycle, which we can see there is no like a hollow region in the large cycle. So if that increases, that helps us to increase the large volume, increase the total volume. And in our case, I will not have any non-perturbative effects, and the volume, we will take a separate type of volume. So this K3 fiber calabiao, which I was showing in the beginning, that is there is a base and there is a K3 fiber. It has it has a similar structure as a toric orientifold. So that's why we can write down the volume as a sandwich of 3-4 cycles. Okay. So now in the perturbative large volume scenario, what people can do is they can add perturbative corrections, which is the standard alpha prime cube correction, as well as this log loop correction. So once I add this, just two of these corrections, one can write down this potential, which is simpler looking, and one can have this large volume scenario. You can see that this is 1 over GS square. GS is the string coupling, which is usually small, and you can see this 0.2 gives this large volume, and this is gives this exponential quantity. But as I said, that it is again an anti-de Sitter, so one has to uplift, and in this scenario, we uplift using a d-term effects. So now what I'm showing you is this what our result is. So here I have not only added d terms, I have also added this higher derivative correction as well as the winding type loop correction. So what I'm doing right now, I'm checking the robustness of this perturbative large volume scenario. So I want to check. So it was already shown and also like well parameterized in our paper that if you just add this, if you just take this piece of this potential and add d terms, you can have inflation. But what is the robustness against adding more corrections, right? So we have added more corrections and checked the robustness. And this B, C2 and C3, they all depend on this GS and W0. Those are the two main free parameters in our potential. And constructing this, giving them some values, we can see that we are still in the weak coupling regime. This is the Euler characteristics, and this X is one important parameter. So X is taking care of this uplift. So because we have from here, from here, we have taken one reparameterization of the fields where we have made them canonical. And after doing this canonical thing, we have the effect coming from this uplift term as a constant parameter. So which is this encoded in this exponential minus x. So if we plug in some number, then we can see we have this nice plots where we have de Sitter shallow potential with minima, maxima, and inflection points. And for so you can change this R1 and R2, and you can play around. And for the inflationary side, if we check their inflationary prediction, then we can see that they are well under control. So PS, which is the amplitude of the power spectrum, is within the bound. Spectral index is 0.96. And R, so one good thing about this model is that look at the value of this gravitational wave, pyramidal gravitational wave, spectral tilt. So it denotes that the field excursion is small. So R is directly, from light bound, we know that this R is directly related to the field excursion. So our field is a small field model, which we know since this is a string theory model building. So it is always good to, for the distance conjecture, this model is within the, it is satisfying the distance conjecture because we know there is a swampland and landscape thing going around. So swampland conjectures. Okay. So now, so this was the volume inflation. So where my phi is the overall volume, overall 60 volume. So this overall 60 volume was expanding and stretching in the space, in our space time, and it was giving me the inflation. So this is volume inflation where phi is a 60 volume. Now I'm going to the fiber inflationary case. That is a second paper. So in this case, my scalar field will not be 60 volume, but a 4D volume. That is the volume of this fiber on top of that base. So I have this three, I will have three moduli, that is tau 1, tau 2, tau 3. And one of them I will replace with the volume because, I can just do that. And I can write this simple potential and note that this exponential does not mean I have non-perturbative effects, but it is just the way, this gamma by phi by 2, it's just the volume. So it just means that there is volume power to the power gamma by 2, for instance. And the CR parameter for our case, we have not been very thorough about it. So we just consider it as a constant. But as I said that in the previous construction, that this X, the uplifting parameter plays, you can consider it as a constant after the dimension, after you get rid of the other scalar fields. So similarly here, you can have this C uplift to play as a constant role, but you can actually assign it with some D-brain uplift or T-brain uplift or D-term uplift. Okay, and this C0, R0 again depends on the string coupling as well as the wave of the superpotential W0. Now again, you can play around and you can plug in some numbers and you can get this nice plots for the potential, which is again shallow and de Sitter. And you can have and you can see that for various values of this R1, that is one of these, one of the constant appearing in front of the volume modulus, fiber modulus, sorry, and they are within the Planck data. And you can again, so these are the model prediction with weak coupling and large volume. So now the volume is even larger than the previous case. So in the previous case, the volume was still a little bit smaller, but now it has larger volume, which is always good. And you have the total, N star is a 50. So we are calculating the total, we were calculating all these parameters at N end minus 50. And you have this power spectrum, which value is well within the bounds, NS is 0.96. And here, this is not a small field model, which you can already see from phi star minus phi n. So this is not a small field model. Again, it is encoded also in the R star, that is a primordial gravitational wave. So what happens, before going to the conclusion, let me tell you the following. So although there is it is not a small field model, but previously it was shown that in this standard fiber inflation, because fiber inflation is one of the well motivated string inflation model. So, but the previous fiber inflation model, they are plagued with a problem, that is the field excursion is bounded from a Kähler cone condition. And that Kähler cone condition is actually deeply rooted in the geometry of the internal space. So how you consider the geometry and you write down your volume, that is encoded in that. So all of these are coming from this string theory side, but in our model, what we have is we don't have it's a jargon. So we don't have a certain exceptional del Bezo divisor. And it is also a reason because we don't have any non-perturbative effects. So we don't need this exceptional del Bezo divisor. So there is no bound on the Kähler. So there is no bound on the field excursion coming from the Kähler cone condition. So we can so the scalar field can roll from any point to another point. So there is no bound, which is one of the good things of our model. So let me conclude. So in these two models, we have shown you that we have shown a concrete global embedding of volume inflation that of this constructed from this perturbative LBS, as well as the fiber inflation. So the volume inflation is a small field inflation, which is always good to look at because of its in accordance with the swamp and distance conjecture. And the second model is a fiber inflation, and again we have shown the global embedding. And not only that, so as I just explained, so it is good to have this field excursion not being bounded by any condition coming from string theory. And yes, so I will thank you for your attention, and I will take questions.
Thank you for the nice talk.